What's going on, everybody? High Peak Education coming back at you once again. This time a video about orbits, namely the orbit of a satellite around the Earth in a uniform circular orbit. So let's read this problem. What must be the linear, that is tangential velocity, maintained by a 500 kilogram satellite as it follows a uniform circular orbit where its height is 4.5 times 10 to the 6 meters around the Earth. The mass of the Earth is 5.98 times 10 to the 24th kilograms. The gravitational constant is given by this, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And we know the radius of the Earth is 6.371 times 10 to the 6 meters. Okay, so first of all, let's go ahead and sketch a picture in some sense of what's going on here. So what I've sketched here is a blue circle representing the Earth. So this is the center of the Earth. And then I've got an orbit of the satellite here sketched as this round circle. So I think the satellite is, we're not told if it's going clockwise or counterclockwise, but let's just imagine it's going counterclockwise from our viewpoint. And let's sketch what the satellite's going to look like. Okay, maybe something like this. Who knows? But this satellite, as it orbits, it's going to experience a certain force. The force it's going to experience is indeed the universal gravity force coming from the Earth. So that should be something like this, directed towards the center of the Earth. So there's Fg. And as long as we assume no air resistance and no frictional forces or anything like that in space, which is not a perfect assumption, but it turns out it's not an absolutely horrible assumption, we can just say this is the only force on the satellite. It's the gravity force. Now, because this thing is in uniform circular motion, we would assume that its tangential velocity, which we can sketch as tangent to the path, like so, so that's its linear tangential velocity, should be a constant everywhere around this circle. Okay. And we should also say that this tangential velocity is always changing direction. It's always tangent to the circle, that is the path, and always about the same value, but it turns out that this tangential velocity continues to change direction. That's because it's directionally accelerating this satellite. So because the satellite is directionally accelerating, the net force on it is a centripetal force. In fact, the gravity force equals the net force, which is going to be the centripetal force. So we can say the following. We can say that the gravity force, which we're mentioning here, should exactly equal to the centripetal force, which has to do with this velocity. So that's going to be the centripetal force. Now, how do we write down this gravity force? Well, we know what the gravity force equation is. It's the universal gravity force equation. So this is going to be big G times little m times me over r squared. Now let's pause and make sure we understand these various parts. I think that big G is the gravity constant that's here. We also note that the satellite has mass little m. So let's go ahead and actually sort of just put that on here. And we also know what little m is. It's a 500 kilogram satellite. How about me? Well, that's the mass of the Earth. So this is Earth, has a certain mass. So this right here is me, mass of the Earth, this number. Okay, and then what about r squared? Now let's label that. That's the radius from the center of the Earth to the satellite. So this distance from the center of the Earth to the satellite is the radius. Now note something important. H, the height, is the distance that the satellite is above the Earth's surface. So don't get that confused. So h being the height is a lot smaller distance than the radius of the Earth itself. Okay? But notice that r, the radius, should equal to the radius of the Earth So that's the radius of the Earth plus the height, plus that height h. So now we've got all the terms on the left-hand side. We know what this gravitational force is. Let's do the right-hand side. So the right-hand side, in terms of linear velocity, v, should be mv squared over r. That's our equation for centripetal force, mv squared over r. Now notice some interesting things go on. Look at this mass of the satellite. Believe it or not, it cancels. How fast the satellite orbits the Earth is independent of the mass of the satellite itself. Next thing, it looks like we also lose one of our r's by cancellation, and we can take a square root of both sides. So we get that the velocity that we're orbiting with, so a lot of times we call this orbit velocity, is equal to the square root of g mass of the thing you're orbiting, in this case the Earth, divided by r. And this is an important equation you should tuck away, because this equation tells us how to calculate how fast something orbits just given what it orbits around and its radius of orbit. So I think we can put in the numbers for this orbit velocity in this case. So let's go ahead and get that. So we have the gravitation constant, that's 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. We multiply that by the mass of the Earth, that's 5.98 times 10 to the 24th kilograms. And we divide that all by the radius, which is the radius of Earth plus the height above the ground. So the radius that of the Earth is given above, that's 6.371 times 10 to the 6th meters. That's about 6,371 kilometers. It's about the average radius of the Earth. Plus the height that the satellite is above the Earth's surface, that's 4.5 times 10 to the minus 6th, or sorry, times 10 to the 6th meters. Okay, I recommend you reach for a calculator here. So I have my calculator in scientific mode. I'm going to do second square root, and then I'm going to do alpha f1 for numerator over denominator. That is a fraction stack. And I'm going to perform 6.67 times 10 to the minus 11th times 5.98 times 10 to the 24th, that's kilograms, that's the mass of the Earth, and we're going to divide that by 6.371, this is the radius of the Earth, times 10 to the 6th, plus the height, the satellite's above ground, 4.5 times 10 to the 6th. Okay, so let's calculate this. Okay, so let's write this down. Looks like it's about 6,060 if we round it to 3 significant digits, or 6.06 times 10 to the 3rd. So 6,060 meters per second. Now note, this is a pretty typical orbit velocity. Most objects that are orbiting are moving about several thousand meters per second, usually on average. So usually 100 meters per second is not enough, and 100,000 or so meters per second is not, that's too much. But 6,000 meters per second seems reasonable for an orbit velocity. So now you know how to calculate how fast something should orbit if it's in uniform circular motion. So thank you very much for your attention. Please smash that like button if you enjoy this content. Please share this video amongst your social networks. I want to thank you for watching High Peak Education. I look forward to reading your comments, and I will see you in the next video.